Alright class, welcome to another lab tutorial of electronic circuit and design, and today in this lab we are going to trace the transient analysis responses for the single stage class B amplifiers. Okay, for this purpose you can fetch the conventional parameters like the 2N2222 version for the NPN based transistor and a personal computer with installed LTspice and few registers that are being required. Okay, now this is the basic circuit diagram of the class B type amplifier, in which we are going to give the input sinusoidal signal at the base of this transistor, and we will get the output from the collector side. Okay, now when I give the sinusoidal input, the class B type amplifier only conducts in the 180-degree conduction region. That means that only the positive side, which is starting from 0 to 180, will be amplified at the output, and for the rest of this cycle, which is in the negative region, that is from 180 degree to 360 degree, will not be amplified. So that is the why we call this class B type amplifier that has the capability to operate only in 180-degree conduction region. Okay, previously when we were actually studying this amplifying the class A type amplifier that is capable to amplify the signal in both the positive region as well as in the negative region. The very important aspect at that time we studied that it usually operate at the Q point. That means that if you are actually supplying this, if you have this signal just like this one, and if you draw the roughly the extended Q point region, the signal will be amplified over here just like this one. Now if I move this Q point toward the extreme point of this VCE region, the point will reach that if you realize this one is this cycle that is being placed from this side to the extreme limit of the VCE. So what will happen over here, that at this region only one of the cycle is being left over here, and the rest of this cycle will be eliminated because you have gone the extreme limit of the cutoff point. So now if you record the value of the collector current at this point, your collector current ICQ will be equal to 0. So this means for class B type amplifier, you need to bias the amplifier at ICQ that is equal to 0. Only in this case the positive cycle will be corresponding to the output side as an amplified, whereas the negative cycle will be eliminated. Okay, now let us just make the simple basic structure using the LTspice by fetching the component from the library, that is 2222, the Q1 NPN based transistor, and let us bias it by using the 10-volt DC. And for the input signal, we have a sinusoidal waveform whose properties are the 1 kHz frequency with amplitude of 4 volts. Okay, we have make a very simple transistor based circuit to demonstrate the class B type operation that we are claiming that the output will be only be amplified or being received only for the 0 to 180 degree. Okay, now this one is my input signal, which is 4 volt peak, and the 1 kilohertz is the frequency, And now just go to the simulation tab, edit simulation command to if you want to set your stop time for the transient analysis. We have here 3 millisecond. Now just simulate it. Okay, this one is my input signal, which is 4 volt peak to peak, and we have connected our load 1.5 kilo ohm, and let's see what we are receiving on this side. Okay, now you can see that okay, now from this figure you can easily realize that the green signal is our input signal, and whereas the blue is the output that has been taken from this emitter side. So if you observe in this figure that there is a difference between the amplitudes, that means the output amplitude is a bit less than that of the input signal. So let us just measure it up. The maximum value is approximately 4 volt, that is exactly 3.99 volts. And let's take the second cursor to measure the difference. That is if you realize it, that this is the voltage amplitude of the green signal, which is 3.997 volt, and the second one is the amplitude of the obtained signal, which is blue in color, that is 3.277. so let's just measure this difference. It's actually 0.718 volts. So where does this difference actually came from? This is due to the fact that it has a diode which consumes the 0.7 volt for the biasing of the circuit. So if you are giving the input signal of 1 volt at the input, the output will be 1 volt minus 0.7, and the remaining of will be given at the output. Similarly, if you are giving here the 4 volt input, 0.7 volt has been consumed between the base and emitter due to the presence of diode. Alright, so this is a basic concern which has the difference. Now let us just try to calculate the efficiency of this circuit. For this purpose, we will use the basic formula, which is efficiency is equal to P out divided by the PDC. So here the P out is actually the 0.5 times the VCQ multiplied by the ICQ. That is, the VCQ is the collector voltage at the Q point. Since we have already discussed that the VCQ is this point, which is equal to that of the VCC voltage. Now in our circuit we have 10 volt DC, so VCQ will also be equal to the 10 volts. Now what is the next function? That is the ICQ, the IRMS value of this ICQ. Now just by clicking on this and using the help of this circuit, which is the RMS is 1.055 milliampere that is being flowing through it. Okay, so just record these values to calculate the overall efficiency of this circuit. Now the PDC is actually equal to VCC multiplied by the collector current. So VCC is the once again the voltage that is being used for the biasing, that is once again 10 volt. Now IC will be the current that will be consumed due to the presence of ammeter resistance. If I take the ratio of P out to PDC, I will get 0.5. that means the efficiency is, now that means that the efficiency of this circuit is only 50%, since the VCQ and ICQ are equal to that of the VCC and ICC at this extreme point. Therefore this factor will be cancelled out, and only the remaining factor will be the this 0.5. Now if I multiply it with 100 to get the overall percentage, that will give me only 50% efficiency. That means that the class B amplifying circuits are only 50% efficient, and through this diagram you can easily visualize as well that only the 50% of the input signal has been retraced on the output side. Now till now you have realized this class B type amplifier which only amplify the signal in only the positive cycle. Now there are some techniques that can be used to also utilize the information being provided by the negative cycle and amplify it on the output as well. So the combination can be formed uh, by connecting the same type of the transistor, one in the NPN mode and other one in as the PNP mode. That means that I'm using the symmetry of one transistor form. So this type of configuration is also called as the push-pull operation that will help us to amplify the or receive the signal from the positive cycle of the input signal as well as the negative cycle of the input signal toward the output side. Alright, now according to this application of using the symmetry, complementary symmetry of the transistor, we can add the two transistor as the NPN and in the PNP mode, and we can bias them with the help of a single source which is the AC input, and we can obtain both the cycles of the input signal at the output. Now how it actually works, it is very simple. When the positive cycle is initiated, one of the transistor, the Q1, is in the closed form. That means the switch become closed, whereas the Q2 is open switch, and we receive the output signal from which the amplitude is 0.7 is points less than the input signal that has been given, as I have also shown you in the class B type amplifying circuit. Okay, now in the second phase, when the negative cycle is given to the input terminal of this the transistor basis, in this case Q1 will now become open, whereas the Q2 will conduct, and in this case we will receive the negative cycle to the output as well. So how it actually looks, it actually just look like this thing. Okay, fine. Now let us discuss the efficiency of this circuit, as we have claimed that our previous circuit for the class B type amplifying was only 50% efficient. However, let's see what is the percentage of efficiency achieved by doing this symmetric analysis. Okay, since the efficiency is only equal to the P out RMS divided by the PDC, where P out RMS is equal to 0.707 times of the V out peak of the signal multiplied by the 0.707 times the voltage at the between the collector ammeter at the Q point. Okay, since the VCEQ is actually equal to half of this VCC voltage, so at that point the IC saturation current will be equal to the VCEQ divided by the load resistance. And lastly, that P out RMS as a whole can be simplified and written as 0.25 times that of the IC saturation current multiplied by the VCC voltage. So finally the average power, which is the PDC, it's actually equal to the IC saturation multiplied by the VCC voltage divided by the 3.14 or by pi. By placing these values of the RMS output power to that of the DC output power, which is the average power, we can easily obtain a result that is 0.25 times of the 3.14 factor, that is actually equal to 78%. Now that means that by utilizing the information from the input signal and retrieving the both the positive and the negative cycles at the output, and by excluding all those losses, just like the those factors like the amplitude was attenuated. If we remove that factor, our output is to with this respect of this circuit is 78% efficient. Alright, now let us try to understand this circuit in which we are using the two transistors. One is NPN and other one is the PNP, and together make it as a push and pull configuration. Okay, now what we have used some voltage divider biasing circuits over here, that is having the resistor R2 and R3, R4 and R5 that are being connected with the base of these transistors, whereas the output is 1.2 kilo ohms, and this is our once again approximate same signal that we have used for the previous configuration as well. And we are also biasing it with the 10 volt DC input. Okay, now let's check it out that what will be the value over the voltage on average over this base, and what will be the value of the voltage on this base. Okay, that's very simple. What you need to do is you need to add up 680 ohms and 680 ohms. That means you are applying the voltage divider rule, and 680 and plus 680 and divide them with the whole swing. That means the sum of 10k 680 and the sum of 680 and the 10k ohm, and let's check what we actually get. Okay, now alright, now if you apply the voltage divider rule to find out the voltages that are going at the bases of this transistor, you just need to find the overall impedances in this region. That means the 680 plus 680 divided by the total impedance in this whole swing. That means the 680 plus 680 plus 10,000 and plus 10,000 as well, and multiply it with the biasing voltage, that is 10 volt, you will obtain 0.636 volt in this region. Now if these two transistors are of the same characteristics, that means the half of the voltage of the 0.636 will be entering at this base, and the half of the voltage will be entering at this base. Now this means your input voltage must be higher than this applied voltage in order to completely bias this whole circuit. Now let us check the output. Okay, now previously what we actually did was we actually supplied the input voltage, a sinusoidal one with a 4 volt peak, and the output was only available for the 180-degree conduction region. Now this is our improved circuit that has the complementary sets of transistors and in the symmetric form, and one is NP, another one is the PNP, and here once again we have this input, and this one is the output voltage across this resistor, that is 1.2 kilo ohm. Now similarly there was a difference of 0.7 volt over here, and let's check it out. What is the difference right now? Okay, for easiness, let us just close the extra simulations to get benefit of the full VN. Okay, now this one is the says the peak across this one. Let's just get the second cursor and let's check it out. It should be 0.7, or let's see what is the difference right now. Okay, it says that it has a difference of 0.371 voltage. That means that the calculation we did over here was correct. The 0.636 voltage was the overall divided voltage in this region, and for one transistor we have to divide it by 2. If we divide it by 2, we actually get 0.313 volt. Now you can also visualize it from here as well, that the amplitude difference is about 0.371 or 371 millivolts. So let us just do some closeness to observe any other kind of difference that we can. Okay, now here is another difference as well. If you look into this structure, you will realize it that due to the 0.7 biasing voltage, the transistor was set off as compared to the input signal, and it was also biased on the late side with the difference of 0.7 volt as well, due to the presence of base 2 emitter semiconducting device that was a diode normally that we consider it as well. So we have also observed this this difference as well, and it can be easily be demonstrated through this demonstration as well. Okay, what does this gap illustrates us? It also tells us that in this region the both transistors are set off, Q1 and Q2 are turned off. Okay, that is the why the difference has been observed over here. If the transistor were highly fast switching, and also there were no sort of any kind of voltage drop between them as well, only in that case we can eliminate this gap as well. So this was the today's tutorial. We have actually clearly demonstrated the class B type amplifier by using a single stage amplifier, and by using the complementary symmetric view of by utilizing the NPN and PNP of the same parameters in connecting them to form the push and pull configuration, in order to utilize the drawbacks that we have actually faced in the conventional B type amplifier. And we have also demonstrated the efficiency of the prior circuit was only 50%, and by developing the push and pull inverter scheme, there you can see the push and pull the push and pull configuration has helped us a lot to achieve the 78.5% efficiency. I hope so that you have really understood this tutorial. If you have any question, just comment in the below section. Also you can email me at hasan.khalid@nfciat.edu.pk. So I wish you best of luck.